I'm so excited. Good afternoon, everyone. My name is Dai Ming. I'm from China. I'm a Chinese boy. No, Chinese man. I've worked at Alibaba, Didi, and Kuaishou. And I've also written books and a course on iOS development. A lot of my work focuses on iOS performance optimization. Today, I will be talking about how to reduce app launch time. I'm firstly explain what app launch time is. Then I will cover how to connect launch time date using tools like instruments, OS signpost, system control API, measure kit, and by hooking message send and Swift functions. I will also go over how to solve common performance issues. Finally, we will drive into advanced way to reduce launch time with optimization strategy and code examples. Let's first understand launch time. Launch time has two main parts, pre-main and post-main. Pre-main happens before the main function. This is when the material file is loaded and the dynamic libraries are read. To optimize here, we can reduce the size of material file and cut down the number of dynamic libraries. Post-main happens after the main function. This is when the UI is rendered and the data is loaded till the app becomes interactive. Here, we can optimize task priorities. So, how can we measure the time spent during the stage? We can use S-code instruments to analyze launch time. The method is to use app launch template instrument, collect data for the first second of the app launch, filter date, and then analyze it, since the launch fast calls many system libraries methods. To get better result, it's important to filter out system libraries data and track time usage per thread. Instruments can do this by setting up call tree to filter system libraries and view data by thread. Keep in mind that the instruments collect data through periodic sampling, so it may miss some details. What are we going to do? So we need to manual analysis. The benefit of approach is that it lets us collect data automatically, gathering it daily. It also allows us to customize the time tracking, like measuring time at the function level, which gives us more detailed states. The thread for the manual analysis include the OS signpost and the measured kit. Let's first look at how to use OS signpost. First, you import os.signpost into your code. Then, where you want to track time and start and end marker to log the duration. Take mark. Data collection with OS signpost is done through S-code's profile feature using the instrument's login template. The limitation of OS signpost is that it can't track pre-main timing. Another limitation is that it still relies on the instrument. How do we solve this limitation? To handle this, we can use the system control system interface to get pre-main timing. And with metric kit, you can gather launch time data without relying on instruments. Let's talk about system control. System control provides an interface to fetch process information. When a process is created, it initializes kernel date and record the creation time. This is the start time of the process. To measure time with system control, we first get process info and then calculate the elapsed time. We do this by setting up system control, create an MIB array, and gathering the p start time value from the k info processing structure. The P start time gives us the process start time. To get the elapsed time, we need to current time and then calculate the difference. This is the code. In the get process running time function, we find the address offset for the current process PID in the process memory layout. This gives us detailed information about the current process stored in K-info. We then get the current time. When the function is called, by subtracting the process start time from the current time, we get the runtime since the process was created. Now that we've solved the issue of not being able to track pre-main time, let's move on to solve how to get the date without relying on instruments. To obtain the pre-main time, you need to first gather information about the process. Extract the process creation time and then calculate the app's running time. Now that we solve this issue of not being able to track pre-main time, let's move on to solve how to get the data without relying on instruments. Oh, sorry. To use metric kit, you first create an MX metric management and add the subscriber to connect date. Data is connected when the app enters the background or when the device is idle. The data processing happens in the MS matrix management subscriber and supports batch processing. You can view the connected data in S-code organizer, and it also supports customer analysis. Manual analysis has many benefits, but it's time-consuming, error-prone, and can need the messy code. So we need an automatic solution. The automatic process involves using tools to pass the code, find method definitions, and insert time logic. This saves development time and makes the code easier to maintain. Tools available for this include source code analysis tools and build integration tools. Next, I will cover some automatic way to measure time, including how to hook match send to track the time of Objective-C function call. For Swift projects, I will explain how to track the time of each Swift function. Let's first see how to track the time of the Objective-C functions. Since all Objective-C functions are called through match send, we can hook this method to track the time of all Objective-C functions. The approach to use fishhook to replace the match send C function. Since match send is written in assembly, we also need to use assembly to do this method replacement. In the replacement, we save the necessary register before the method call and restore them afterward. We track the time before and after method call, save the time for each function, and generate a report. We can view the full code at the link below. Here's the code in the SM call tray start function. We use fishhook to rebound symbols to replace the method. The original message send is saved as Objective-C message send, and the hook logic is the hook Objective-C message send. In the hook Objective-C message send method, we first save the method call parameters, then record the start time with the before Objective-C message send. After reading the parameters, we call the original Objective-C message send. Save it return value and calculate the function execution time. Finally, we return to the value of Objective-C message send and wrap everything in an interface to easy use. After running it, you will see the execution time of all functions is recorded. The code summary is shown in the diagram. We first replace the message send and calculate the time execution time in the replacement. Then we save the data and generate a report. This is the method we used in our company to check the startup time. This method only works for tracking the execution time of Objective-C function. But what about the Swift functions? To track the runtime of Swift functions, I load a tool. Simply drag your Swift project folder into the tool. Click a button, and the tools will pass the Swift files in the project and find function definitions and insert the time tracking code. When your app runs, the tools start collecting data, including function name, call count, and execution times. This is the tools interface. Just drag your project in. In the top right corner, there's a button for the time tracking. Click it, and it will insert the tracking code. Once your project runs, the tools will sort the function's execution time, showing the average time, call count, and the total time for each function. From what we've covered so far, we know how to identify where startup time is spent. There are few common issues that can impact launch time. There are several common situations that can affect function execution time, as shown in the image. The first one is expensive operations, like reading large files, making network requests, and querying the database. The solution here is to move these operations to the background or break them into smaller tasks that run as needed. The second issue is displaying large image. You can assign, load, and decode large image using Swift concurrency, or use more optimized format to reduce I/O and memory usage. The third issue is frequent UI updates. The solution is to use lazy loading to only update the UI visible on the screen, and use default placeholder to UI element off screen. The last issue is dispatch semaphore, which can block the main thread. The solution is to use Swift concurrency task group, moving the weight into assigned task, and free up the main thread. The relevant example and solutions are available in the link below. In the demo app, I've included all the bad case. The app launch time was huge, over 10 seconds. After optimizing the code, the main thread finish time is down to just 1 second. And then assigned completion time is also much shorter. You definitely want to download this demo and see the difference before and after optimization. The link is below on the page. We've used the tools to pinpoint startup issues. And now we've solved those costly problems. But can we further reduce the startup time? Next, I will introduce 2 more technical that can reduce startup time even further. Optimizing the launch path and merging libraries. The principle of launch path optimization is that when an external launch is triggered, we bypass the home page's reading and rendering, directly open the target page. The benefit of this approach is that it saves the overhead of reading and rendering the home page. Next is the mergeable library optimization technical. Traditionally, dynamic libraries were loaded only one by one, processing symbols and then initialize each libraries. Which, with mergeable libraries, dynamic libraries are merged, removing the redundant and duplicate symbols and turning them into static libraries. This is a new feature in Xcode that can be enabled through built-in settings. The setting is very easy. In built-in settings, you can find the merged binary option and set it to automatic. That's all. At this point, we've identified the problems and understand how to address them. We also know how to further reduce startup time. However, as the app evolves, the tasks that run during startup can become more complex and numerous. We need a way to manage this task effectively so we can control the system resource usage during the startup time and prevent the launch time from getting worse. CPU and memory are limited resource. If we don't manage multi-threading task properly, tasks can pile up at a time, causing the CPU to switch between the threads frequently, which wastes time. When threads aren't busy, the CPU isn't fully utilized, causing delays and slowing down startup time. The larger the code base, the more obvious this issue becomes. So how can we better manage multi-threading tasks and make full use of the CPU? We divide tasks into high priority and low priority ones. High priority tasks should run concurrently and can have dependency management. Low priority tasks can be delayed and run only system resources are available. I create two functions: execute tasks concurrently and perform low priority tasks. Execute tasks concurrently, run high priority tasks concurrently, using Swift concurrency with task group, and the order of calling this function control task dependencies. Perform low priority tasks, run low priority tasks using task.detached, and set the task's priority to background. Once we create 3 high priority task groups, they will execute sequentially, and tasks within each group will run currently. Low priority tasks will run when system resources are free. So far, we mostly covered post-man optimizations. For pre-man, we can optimize startup time by reducing the app size. There are many ways to reduce app size, many through static analysis. Today, I will show how we can analyze at the runtime to find the unused code, expanding the scope of our optimizations. Let me introduce a solution that can help identify which classes are not being used during runtime. The process involves checking all classes when the app goes to the background and determine which one has been initialized. We use the getClassList API to get a list of all classes, and NS class from string to find the meta class of each class. The meta class's flag field, when shift 29 bits, tells us if the class was initialized during the runtime. In the code, meta class struct state method return a class RWT meta class struct. The flag field is shift left by 29 bits. A value of 0 means the class hasn't been initialized, while 1 means it has. In the initialized class in array method, we use the NS class from string to get class state, then call initialized to check if the class was initialized. We add initialized class to an array, and the remaining classes are the one not used during this app session. Here, I've printed all the initialized classes. It's also how we checked for unused code in our company. From the results of the analysis, this solution includes detect a lot of unused code, especially older code. However, there's one issue. If a class contains many functions, as long as one of them is used, the entire class is considered in use. So we need to take it a step further and find even more unused code. Do you remember the tools I created connect Swift function date? That tools can also connect date on all functions in your app. Every function your app call during execution gets logged. By subtracting the functions that are actually called from the total list, we can identify unused functions. In the tools, just click the button in the top right corner of the tools, and it will show a list of all functions, with the ones that were executed marked. That's all for today. We will go over the built-in tools in Xcode for checking startup issue and how to create customer tools for automating the checkings. We also look at some bad case and discussed optimization technical. To make every millisecond count, we share more practical optimization tips. I hope you find this helpful. Thank you for watching.